So we began discussing some aspects of data in the last class. We looked at define what is a data object and how do you represent it and different types of attributes and things like that. So we'll see more of that in the next class also. So we also described some measures of describing data, summarizing data, right? What is central tendency, what is spread, right? We looked at 5-number summary and things like that, the box plot and other things. So some of the things we saw in the last class are very simple representations of data, right? Like box plot, which is quite intuitive and quite simple. Now let us look at more sophisticated ways of representing data, which makes it intuitive. Sometimes you have to incorporate domain knowledge also in your depiction of data. So, and there it becomes more like an art than a science, right? So what are some, let's look at some examples of more advanced ways of data visualization. So why do you want to visualize data? First of all, to gain insight into the information space, right? By mapping numbers onto some kind of a graphical primitives, right? Then provide qualitative overview, right? Because if you just look at a spreadsheet, it's very difficult to understand what's happening with the data. But if you look at some pictures, you can get some qualitative understanding of some of the trends in the data. Then look for patterns, trends, structure, etc. when you depict it in some visual form, or help for interesting regions and suitable parameters, etc. etc. So how do you visualize in low dimension? Because when you visualize, obviously you have to visualize in low dimensions only because right beyond 3 or 4 dimensions is very hard to visualize. So let's look at some low dimensional examples. Here is an example of 1D data which is visualized. The specific data is visualizing, let's say, spectrum, or more specifically solar spectrum, right? And you know how to visualize spectrum, right? You can just make a plot of if you look at this picture here, so y-axis is the power and x-axis is the frequency, so you can depict the spectrum like this. But in this case they are not depicting solar spectrum like this, they're using this kind of a color bands. Why is it done? What is the advantage? So if you look at it more carefully, you see these black lines right in the middle of spectrum. The whole spectrum is interspersed with black lines, and you see that the black lines are very thin lines. So the thing is, we know that in solar spectrum you have a continuous spectrum, and then which is interspersed by these thin black lines, which indicates an absence of energy at certain very specific frequencies. So if you have to depict that as a continuous graph, it becomes somewhat problematic, because you'll have a continuous curve with very sharp gaps like that. But if you plot that in a graph, it looks very weird. It's not intuitive at all, because this gap is a very thin line. So instead of depicting it in a traditional fashion, like a graph, this is a very innovative way of depicting that data. It's basically power spectrum is depicted like this. That thin line can be very easily seen in the background of some colored region. So that is one point. Secondly, the spectrum, in this case we are talking about visible spectrum of the solar spectrum, and visual spectrum is associated with some colors. So it would be nice to show those colors in the visual depiction instead of just showing it as a graph. So that's what is done here. The bigger colors of visible spectrum are shown here, so it is more intuitive, and also it looks good. So using color to actually indicate different spectral bands, and showing the dark lines as black lines, and showing the absence of energy at certain specific frequencies as black lines or dark lines, are some innovative features which are very appropriate for this particular data set. This is an example of domain knowledge-based visualization. Similarly, microarray data. In microarrays, as you know, if you're in biotech, you have small wells in which your probe interacts with a bunch of target molecules, and the level of interaction produces some kind of a response signal, and whose intensity is encoded in the form of some kind of a color, right? So this picture actually looks like a microarray, right? So it is in that sense it's borrowing some features from the domain, and is also a numerical depiction of some 2D array. So in 3D you can have more sophisticated visualization forms. So visualization means generally you're talking about an image, something that is visual means an image. But if you want to depict 3D, you can. So when in human vision, since we see with both eyes, right, we use some kind of stereoscopy to integrate the retinal to retinal images and construct a 3D percept, right? But we also get 3D information from other sources of the input image, like occlusion and perspective and things like that. So in this kind of 3D visualization, it is done in you can interact with the object by using some kind of a device and rotate it, move it around, so they can get a 3D understanding of the object better. Okay, so then let us look at histogram. We have already seen some simple way of looking at the distribution using histogram. But histogram is good for only scalar data, right? But what if you have multidimensional data? How do you depict that? So you can do that using a bunch of histograms, as it is done in this case. Here the example data is what is called iris data. It's a well-known data set used in a lot of pattern recognition literature. So this data comes from a bunch of flowers called iris, as a family of flowers. There are 5 kinds of flowers. Each flower class has 4 attributes. The attributes are petal length and petal width, then sepal length and sepal width. So then the 50 samples per each flower type. So actually there are only 3 kinds of flowers, right? Setosa, versicolor, and virginica, and there are 4 4 attributes. Since there are 4 so there are so for each attribute and for each flower you can have a separate histogram. Like we said, for each flower there are 50 example data and 4 dimensions, right? So in this picture you can see, look at so there's a bunch of squares here. It's some kind of a lower triangular matrix, right? So now look at only the diagonal panels, diagonal squares. In each of these squares in the diagonal there are 3 histograms. You can see that in 3 colors. Each color represents 1 flower type, 1 flower class. So the red is Setosa, blue is versicolor, and green is virginica. So if you take only sepal length, what's the histogram like for the 3 flowers? That is shown in this square. Then sepal width, 3 histograms, petal length, 3 histograms, and petal width, 3 histograms. So now they have drawn in this picture scatter plots, right? So scatter plot is plotted against 2 variables. So in this case, the idea is to understand how different the flowers are by comparing the corresponding features. So in terms of sepal length, how different are they? In terms of sepal width, how different are they, and things like that. And so here you see that you see the scatter plots are drawn, comparing different attributes for all these 4 attributes. And once you draw the scatter plot, they've also fitted lines through the scatter plot. Since there are 4 features, right? If you draw the combinations, you have 4 by 4. But since it's symmetric, it's enough if you just look at the lower triangular matrix. So here you see all possible scatter plots and lines fitted through them. Next visualization is a Pareto chart. A Pareto chart is a graph that indicates the frequency of causes of a certain phenomenon. And also the frequencies are ordered in terms of lowest frequency to highest frequency or vice versa. So that tells you if you have a phenomenon, what are the causes and which are more important causes, and how do they all add up in producing that phenomenon. Okay, so that will let you prioritize the causes, and then you can try to fix the more important causes first, right, before in your approach to solve the problem. So take this example. So why do employees come late to work? Right? If you look at different kind of different causes of that, one is the traffic, and traffic seems to be the major factor. Because whatever some 55% of the cases of delayed arrival is because of traffic. Next is childcare. Next is public transportation. Okay, so next is weather, right, etc., etc. Next is oversleeping, etc., etc. So among these, emergencies are rare, so the company doesn't have to do anything about it. Right, weather is not that frequent. Also, you cannot change the weather. But one thing that you can do, traffic also, it is difficult to control unless you encourage people to take the public transportation, etc. Right, you have no control. Company has no control. But what the company can do about childcare is maybe have a crush within the company building itself, so that people can bring their children and leave them there. That will save some trouble arising due to childcare responsibilities. So like that, if you can list out different causes and look at the relative frequencies, then you can prioritize and see which is the most important cause, and see then you can attend to them if possible in that order. Then scatter plots we already seen. These are
Hello,
scatter
sir.
plots. Hello, yeah.
In the previous slide,
This one.
what is this on left side, the number 168.0?
The frequency of occurrence, that is, so totally there are 1, 2, 3, 4, 6 causes, right? So there are 100 cases of late arrivals, let us say. Among them, how many of them are coming late because of traffic problems? How many are coming late because of childcare issues? How many coming late because of public transportation problems?
So how frequency will be in point means?
No, the percentages. On left side,
Is percentage and right
yeah,
side?
I'm not sure. I think they must have taken the original number of cases and just divided that, converted the percentage.
Have taken cases, it
This
should
is
not
probably
be in point.
I'm not sure. Maybe the actual delay in terms of minutes or something, right? How much was the delay? What's the average value? Maybe that was in terms of minutes. Right? But I have to look up. It looks like it is a delay in terms of minutes.
Okay.
Okay, so these are scatter plots. You already seen this. Then let us look at correlation. So if you have two sets of data, xi and yi, right, and you want to see if they are correlated. So the one is well-known measure of that correlation is Pearson correlation coefficient, given by this formula: sigma xi minus x bar. X bar is the mean of xi times yi minus y bar divided by n minus 1 into sx sy, which is the standard deviations. That expanded out in the right formula, right? Product of standard deviations. So now the thing is, if you see the examples in the graphical examples in the upper part of the slide, so you see that, take the first column, right? So just to show that it will only capture linear features, linear correlation features, but not higher order correlation. For example, look at the first column. You see that both x and y are linear, almost linearly related, and correlation is 1. In the first column, second row, right? The features are all linearly related, but the slope is different. So take the second row. In all the cases on second row, the two variables x and y are linearly related, but the slope is different. But the coefficient is the same, so it doesn't distinguish between the high correlation. I mean, between high slope and low slope, because high slope is different from low slope, right? But the way they define the correlation coefficient is defined, it doesn't distinguish it. That's what it's trying to show. Similarly, if you look at the first row, you see that if you first row go to the middle column, right? If you look at the scatter plot, doesn't show any correlation between the two variables, and therefore correlation you're getting it to be 0, which is intuitive. So this is the case where the Pearson correlation coefficient gives best result. It's very intuitive and it satisfying. But the problem with it is it's not sensitive to the slope. And you see also negative correlation when one is increasing, other is decreasing, you get negative correlation, as you can see in the first row. And in second row also you get negative correlation. But since the two variables are linearly related, right? If the slope is negative, you get a correlation of -1. Slope is positive, you get a correlation of +1. But there is no graded variation based on the slope. Okay, that's the problem with Pearson correlation coefficient. And also intuitively, zero correlation means that there is no particular relationship between these two variables, right? That is what that is the story the first row is telling. But the problem is sometimes the two variables can have very complicated relationship, which can only be captured by a nonlinear model, but it cannot be captured by Pearson this correlation coefficient, as you can see in the lower row, bottommost row, where in this case the two variables seem to have some complicated relationship, right? But the coefficient doesn't capture that. Okay, it just shows zero correlation for all of them, but they have the distribution has some interesting structure, and that is not captured by the correlation coefficient. So the scatter plot with the examples that we have seen so far are all in 2D, but you can also have scatter plots in 3D, like this example. And you can also visualize spatial data and spatial temporal data. For example, this is a contour plot. It's simply a scalar image of a scalar quantity. But so basically, you're supposed to see which regions have high value, which regions have low value, and things like that. So you can show that using color plot, which makes the plot more interesting. Here, in this case, red is high value and purple is low value or negative value, and yellow is close to 0, yellow and green. So you can see that. But in addition, they have also added contours. So contours are like, we have talked about level curves, I think a couple of classes ago. So level curves are where this the function, so you have some function z is equal to f of x comma y. So take the cases where z is equal to some. So let's take the function z is equal to f x comma y. So take the cases where f x comma y is equal to some c. Okay, that will give you a level curve, and this is the curves that you get in the process are your contours. Okay, so here in addition to the color plot, they also added contours, so that will give an idea of where all the value of the function is constant. Another thing is surface plot, like it's more revealing because you can see the 3D and all. But you can also, the other problem is it occludes. So there you can see two hills here and here, but there's small features behind those hills, you cannot see them, right? But you can see them in this plot. So there's like that. There's an advantage, disadvantage in different kinds of visualization. So the two examples we have seen before are scalar plots. These are scalar fields, right? There's only one scalar value depicted as a function of some space x and y. But if you want to depict a vector, right, a vector field, right, you cannot do it like that. So this is an example of depicting a vector field. So at every point you are depicting a vector. So in this case, you see a nice circulation right around the center. So if you calculate curl, you might have studied that in your vector algebra, vector analysis class before. You can see a high value of curl in the center of this vector field. So other examples of, so this is a 2D vector field and this is a 3D vector field, where at every point in 3D space you depict a vector. Now beyond 3D, it's very hard to visualize, but people have come up with some innovative ways of depicting high dimensional data also. So again, if you take the iris data, so you have 3 flowers and each, there are 4 features. So how do you depict that, this 4-dimensional data, and showing the 3 clusters that is corresponding to the 3 flowers? So here what they have done is something very interesting. It's called a parallel coordinates plot. So they've taken each of the 4 features, right? That is 4 vertical lines, Now let's take one flower, Iris setosa, and use purple color to denote this flower. Now take all the sepal length values for this flower and mark them like this. Okay, and similarly take the corresponding sepal width values of the same flower and mark them as points on this vertical line, second vertical line. Similarly, petal length on this vertical line, petal with vertical line. Now, for a given data point, since it has 4 dimensions, you'll have 4 corresponding points, right, on each of these lines. Now connect them using a purple line. Okay, so that will be some kind of a piecewise linear line, or a piecewise linear curve. That line with all these bends, one line indicates one flower or data of one flower. So each flower has four features, right? Each of these features gives you a point on each of these lines. So connect those lines using a colored line, a piecewise linear curve, right? And that curve indicates one flower. So like that, you'll have a bunch of purple piecewise linear curves to indicate all the iris setosa flowers. Similarly, you have a bunch of navy blue curves for iris virginica and bunch of green or whatever this color is, right, for versicolor. So there's a lot of occlusion because when one line goes or another line, you can, they tend to occlude each other. But by and large, you can see what is different about these 4 flower classes, right? And how are the parameters different? So, for example, you can see that from this picture, you can make out that if you ask which feature is most discriminative among the 3 classes, you can see immediately that petal length is very discriminative. Yes, all 3 flowers have fairly different petal lengths, but sepal width is very similar. All 3 have very similar values. In terms of sepal length, right, the purple is that is iris setosa is different from both iris versicolor and iris virginica. Iris virginica and iris versicolor are very similar for sepal lengths because you see a lot of occlusion going on here. Similarly, petal width is also quite distinctive for the 3 flowers. So on the whole, petal length and petal width give you more discrimination, but sepal length and sepal width are not that discriminative. Okay, right, because for both versicolor and virginica, the sepal width and sepal length are very similar. So all those things you can simply read out of this one figure, although the data is 4-dimensional. Using this innovative kind of visualization, you can distinguish the 3 classes. Another example like that is what is called a star coordinate. But with the star coordinate, you can only depict one data point and all its dimensions. Right? How do you do that? Because here you have 4 dimensions. Right? The way you draw it is take a coordinate system which has 4 axes, meaning 2 axes, x plus x minus, y plus y minus. So the 4 points you plot like this. Sepal length you plot on the positive x-axis. Sepal width you plot on the positive y-axis. Right, petal length on the negative x-axis, petal width on the negative y-axis. So once you have these 4 points, connect them using a polygon. Okay, this polygon now indicates that one data point. But unlike the previous one, where you can plot many data points in the same graph, in this depiction you can only plot one data point at a time. If you plot many things on the same coordinate system, it will look more messy, but you can try that. Because the objective of the star coordinates is only to depict one high-dimensional data. So if you have more dimensions, then you can have more. Like if you have n dimensions, you can divide the entire circle into n sectors, right, and then depict them like that. Okay, so even more innovative ways of depicting multidimensional data is what's called Kernoff Phases. So basically, in this case, you use the high-dimensional data, the vector data, and use each feature value to encode one property of this phase, which is like a cartoon of a phase. So for example, the sepal length is, this is quite arbitrary. It's more like an art than a science, right? The sepal length in this case is used to denote the size of the face, and sepal width to denote the forehead to jaw ratio. Petal length to denote the shape of the forehead, and petal width the shape of the jaw. So with all this, you see that Virginica flowers look like this long face. Versicolor flowers, look like this. Again, long face, I don't know. The Satoshis are all very short, faces. And you can go overboard and take more dimensions and map it onto more features of the face. These are interesting and even funny, but beyond that, there is not much. I don't see much practical use, right, in such depictions. It is interesting. Another example of multi-scale visualization. So let's say I have some time series, right? And something is varying with time, and that variation is happening at multiple time scales. So on the time scale of hours in a given day, and and over weeks and months over a whole year. Now, if I just plot that as a one long graph of variation going from 0 to 365 days, it's very hard to make out, especially if I have data going at the scale of even minutes, that is within a given day. It's very hard to make out from that what is the variation that's happening within a day, and what is the variation that is happening over months or over weeks. All right. So for that, this is a very interesting way to. So these are all very specific depictions. These are not like, so for example, a graph is very generic. You can plot any y against any x, right, and make a graph. But this is a very specific domain-specific data. It will be applicable only to that particular kind of data, so for that particular kind of a purpose. So in this case, the top left depiction gives you a variation of the quantity within a day. So within a week, and even within a day. So on the columns, you depict the days of the week. There's Montag, Dienstag, Mittwoch, and there's German words for days of the week: Monday, Tuesday, Wednesday, and all that. And within that, you can see. So what is the variation within that? And in this case, you also see the variation at within the day level of minutes. So this is basically the top left is like this is hours, student day is hours, right? And within that you also see minutes, right? Within the hour, in the top right, bottom right picture. Now circle segments display similar to the star coordinates I've just shown, but with a slight difference. That is, so if I have n dimensions, in this case I have 7 dimensions. Okay, I'll have 7 radiating lines, okay, to depict each of the 7, and I'll have 7 sectors, right? 1, 2, 3, 4, 5, 6, 7 sectors. A given data point has to be depicted within the 7 sectors. So the value of the data point, the value of each feature, is mapped onto some color. Okay, and and each data point with all its dimensions is one polygon. So for example, if I take this, if I draw a polygon at certain distance from the center, right? So that polygon, so in this case a heptagon, like a 7-side polygon, represents one data point. That is all its 7 features, right, depicted by the 7-side polygon. Now, how do you indicate the value of each of the features? By that color. For example, here and here it's kind of green. Here it is more purple. Here also it is purple. Here it is green. Here is purple. The purple and green indicate some numbers, some magnitudes. So like that, this polygon indicates that vector. So similarly, if you have lots of data points, then they're all shown as a whole set of polygons of increasing sizes, right? So the size of the polygon doesn't indicate the numerical value. It is the color of the lines that indicates the numerical value. Okay, so like that is one way of depicting multidimensional data. This is called circle segment display. Okay, so one more thing is called circles, and the circles is very nicely depicted in this context, in this example, where it shows airlines, right, and the air traffic connections between different world cities. So if you want to show the connections between different world cities, you can show it on a world map like this, as this top right figure. But it looks very messy, because the thing is, if you have n cities, right, in principle, the number of connections will be order of n square. Okay, so you need to, so your depiction of these connections should reflect this fact. We may not have, every city may not be directly connected to every other city, right? So it won't be actually n square, it will be less than n square, but it's likely that it is order of n square. So in the circles, they're making use of the property of the circle to depict this kind of data very nicely, because in circle the circumference, right, is proportional to radius, whereas the area of the circle is proportional to radius square. So making use of this feature of the circle, they depict this like this. All the cities are depicted on circumference, and all the connections go through the center of the circle. And also, if two cities are connected more often with more airline, more connections, then you move the two cities closer, right, on the circumference, so that you don't occupy too much space. So like that, so it's a very innovative way of depicting cities and their connections using this kind of circle plot. It's called the circles. Another example is dimensional stacking. So it shows the visualization of oil mining data with longitude and latitude mapped onto the outer x and y axis, and ore grade and depth mapped onto the inner x and y axis. So because in this case actually 4-dimensional data, it is shown using a grid plot, but there is a nested structure in this grid plot. There is outer grid, right, shown by this. So where each of these is one unit, okay, this bigger thing, and within each of these boxes, there's again a smaller grid, right? So the outer grid indicates the latitude, longitude, and and what is the kind of a quality of ore grade and ore depth that is shown inside the inner grid. Then finally, there is cone trees, which depict hierarchical data as cones. So in your hierarchical data, you have some kind of suppose you are depicting organizational chart of a company. So there is I don't know, the CEO or somebody like that at the very top. Then you have a bunch of senior vice presidents, and then there is senior managers, and then there is middle managers, etc., etc., and the employees, etc., etc., right? So this kind of organizational chart, you can depict it as a tree like this, what I've just drawn, but you can also depict it as a cone tree, which gives you more room to depict the entities. If you have, the tree is very complicated, like in this case. So in this tree that I've drawn, at each level it's a straight line. All the nodes are arrayed, in a single line. So if you have a lot of nodes, there's not much space. So you see that I'm already having problem packing enough nodes. But whereas instead of depicting as a row of nodes, depict them as a circle. Okay, that means, so if a point is connected to a circle, right, it becomes a cone. Okay, so then at each point, if you are connecting to another circle, you get a kind of a network of cones like that, right, which is what is shown here. And the problem with this is some of the nodes are uploaded, some are in the background, some are in the foreground. So with a little bit of animation and all that, you can, right, you can come up with some ways of rotating the cones, right, like the way you move the, right, if you have a bunch of shirts, right, on a hung over some hangers. You can move the hangers back and forth and create space in a cloth store, right? You can move the hangers back and forth and see some shirts which are deep inside the row and things like that, right? So similarly, in the cone tree plot, you can add some animation to this. I can rotate the cones, and whatever is invisible and uploaded, I can bring it to the foreground, right? So this is a more fancy way of depicting an organizational chart. Or another kind of cone tree, right? This is static, but the advantage of this is you can see the connection from somebody at the bottommost rung to the very top of the cone. So you can see it like a pathway that connects any point anywhere in this cone tree to the very top. And especially if you take a top view of this cone, as it is shown in the bottom figure, you can see the path that connects any point in the organizational tree, right, to the apex. So, that finishes this discussion of visualization. I want to show you. Okay, but this will take some time. So I want to show you a video of this guy called Hans Rosling. He makes it very interesting how to. So he shows how you can make visualization of data, complex data, multidimensional data, very interesting. But I need some time. So let me see how long is this. It's 20 minutes. Do we have 20 minutes? Can watch it now, or shall watch it next class?
Yeah, we have 15 minutes officially.
So guys, if you don't mind staying for 5 minutes extra, this is a nice TED talk. Or shall watch it in the next class?
Okay, sir. Continue.
Okay. So let me share that tab. No, stop presenting. Share the tab. So you can see the video, right?
Yes, sir.
And you can hear the video sound also, right?
About 10
Yes,
years
yes,
ago,
yes.
I
Okay.
took on the
Yes, sir.
task to teach global development to Swedish undergraduate students. That was after having spent about 20 years together with African institutions studying hunger in Africa. So I was sort of expected to know a little about the world. And I started in our medical university, Karolinska Institute, an undergraduate course called Global Health. But when you get that opportunity, you get a little nervous. I thought these students coming to us actually have the highest grade you can get in Swedish college system. So I thought maybe they know everything I'm going to teach them about. So I did a pre-test when they came. And one of the questions from which I learned a lot was this one: which country has the highest child mortality of these 5 pairs? And I put them together so that in each pair of country, one has twice the child mortality of the other. And this means that it's much bigger the difference than the uncertainty of the data. I won't put you at a test here, but it's Turkey, which is highest there, Poland, Russia, Pakistan, and South Africa. And these were the results of the Swedish students. I did it, so I got a confidence interval, which was pretty narrow, and I got happy, of course. I had 1.8 right answer out of 5 possible. And that means that there was a place for a professor of international health and for my course. But one late night, when I was compiling the report, I really realized my discovery. I have shown that Swedish top students know statistically significantly less about the world than the chimpanzees. Because the chimpanzee would score half right. If I gave them 2 bananas with Sri Lanka and Turkey, they would be right half of the cases. But the students are not there. The problem for me was not ignorance, it was preconceived ideas. I did also an unethical study of the professors of the Karolinska Institute that hands out the Nobel Prize in medicine, and they are on par with the chimpanzee there. So this is where I realized that there was really a need to communicate, because the data of what's happening in the world and the child health of every country is very well aware. So we did this software which displays it like this. Every bubble here is a country. This country over here is this is China. And this is India. The size of the bubble is the population. And on this axis here, I put fertility rate. Because my students, what they said when they looked upon the world, and I asked them, what do you really think about the world? Well, I first discovered that the textbook was Tintin mainly. And they said the world is still we and them. And we is Western world, and them is third world. And what do you mean with Western world? I said, well, that's long life in small family, and third world is short life in large family. So this is what I could display here. I put fertility rate here, number of children per woman, 1, 2, 3, 4, up to about 8 children per woman. We have very good data since 1962, 1960 about, on the size of families in all countries. The error margin is narrow. Here I put life expectancy at birth, from 30 years in some countries up to about 70 years. And 1962, there was really a group of countries here that was industrialized countries, and they had small families and long lives. And these were the developing countries. They had large families and they had relatively short lives. Now, what has happened since 1962? We want to see the change. Are the students right? It's still 2 types of countries? Or have these developing countries got smaller families and they live here? Or have they got longer lives and live up there? Let's see. We start the world. And this is all UN statistic that has been available. Here we go. Can you see there? It's China. They're moving against better health. They're improving there. All the green Latin American countries, they are moving towards smaller families. The yellow ones here are the Arabic countries, and they get larger families, but longer lives, but not larger families. The Africans are the green down here. They still remain here. This is India. Indonesia is moving on pretty fast. And in the 80s here, you have Bangladesh still among the African countries there. But now Bangladesh, it's a miracle that happens in the 80s. The imams start to promote family planning, and they move up into that corner. And in 90s, we have the terrible HIV epidemic that takes down the life expectancy of the African countries, and all the rest of the world moves up into the corner where we have long lives and small family, and we have a completely new world. Let me make a comparison directly between United States of America and Vietnam. 1964. America had small families and long life. Vietnam had large families and short lives. And this is what happens. The data during the war indicate that even with all the death, there was an improvement of life expectancy. By the end of the year, the family planning started in Vietnam, and they went for smaller families. And the United States up there is getting for longer life, keeping family size. And in the 80s now, they give up communist planning and they go for market economy, and it moves faster even than social life. And today we have in Vietnam the same life expectancy and the same family size here in Vietnam 2003 as in United States 1974 by the end of the war. I think we all, if we don't look in the data, we underestimate the tremendous change in Asia, which was in social change before we saw the economical change. So let's move over to another way here in which we could display the distribution in the world of the income. This is the world distribution of income of people. $1, $10, or $100 per day. There's no gap between rich and poor any longer. This is a myth. There's a little hump here. But there are people all the way. And if we look where the income ends up, the income, this is 100% of world's annual income. And the richest 20%, they take out of that about 74%. And the poorest 20%, they take about 2%. And this shows that the concept developing countries is extremely doubtful. We sort of think about aid, like these people here giving aid to these people here. But in the middle, we have most of the world population. And they have now 24% of the income. We heard it in other forms. And who are these? Where are the different countries? I can show you Africa. This is Africa. 10% of the world population, most in poverty. This is OECD, the rich country, the country club of the UN. And they are over here on this side, and quite an overlap between Africa and OECD. And this is Latin America. It has everything on this earth, from the poorest to the richest in Latin America. And on top of that, we can put East Europe, we can put East Asia, and we put South Asia. And how did it look like if we go back in time to about 1970? Then there was more of a hump. And we have most who lived in absolute poverty were Asians. The problem in the world was the poverty in Asia. And if I now let the world move forward, you will see that while population increase, there are hundreds of millions in Asia getting out of poverty and some others get into poverty. And this is the pattern we have today. And the best projection from the World Bank is that this will happen. And we will not have a divided world. We will have most people in the middle. Of course, it's a logarithmic scale here. But our concept of economy is growth with percent. We look upon it as a possibility of percentage increase. If I change these and I take GDP per capita instead of family income, and I turn these individual data into regional data of gross domestic product, and I take the regions down here, the size of the bubble is still the population, and you have the OECD there, and you have sub-Saharan Africa there, and we take off the Arab states there, coming both from Africa and from Asia, and we put them separately, and we can expand this axis, and I can give it a new dimension here by adding the social values there, child survival. Now I have money on that axis, and I have the possibility of children to survive there. In some countries, 99.7% of children survive to 5 years of age, others only 70. And here it seems that there is a gap between OECD, Latin America, East Europe, East Asia, Arab states, South Asia, and Sub-Saharan Africa. The linearity is very strong between child survival and money. But let me split Sub-Saharan Africa. Health is there, and better health is up there. I can go here, and I can split Sub-Saharan Africa into its countries. And when it bursts, the size of each country bubble is the size of the population. Sierra Leone down there, Mauritius up there. Mauritius was the first country to get away with trade barriers, and they could sell their sugar, they could sell their textiles on equal terms as the people in Europe and North America. There's a huge difference between Africa, and Ghana is here in the middle. In Sierra Leone, humanitarian aid. Here in Uganda, development aid. Here, time to invest. There you can go for holiday. It's a tremendous variation within Africa, which we very often make that it's equal everything. I can split South Asia here. India is the big bubble in the middle, but huge difference between Afghanistan and Sri Lanka. And I can split Arab states. How are they? Same climate, same culture, same religion, huge difference. Even between neighbors. Yemen, civil war, United Arab Emirates money, which was quite equally and well used. Not as the myth is. And that includes all the children of the foreign workers who are in the country. Data is often better than you think. Many people say that data is bad. There is an uncertainty margin. But we can see the difference here, Cambodia, Singapore. The differences are much bigger than the weakness of the data. East Europe, Soviet economy for a long time, but they come out after 10 years very, very differently. And there is Latin America. Today we don't have to go to Cuba to find a healthy country in Latin America. Chile will have a lower child mortality than Cuba within some few years from now. And here we have high-income countries in OECD, and we get the whole pattern here of the world, which is more or less like this. And if we look at it, how it looks the world, in 1960, it starts to move, 1960. This is Mao Zedong. He brought health to China. And then he died, and then Deng Xiaoping came and brought money to China and brought them into the mainstream again. And we have seen how countries move in different directions like this. So it's sort of difficult to get an example country which shows the pattern of the world. But I would like to bring you back to about here at 1960. And I would like to compare South Korea, which is this one, with Brazil, which is this one. The label went away for me here. And I would like to compare Uganda, which is there. And I can run it forward like this. And you can see how South Korea is making a very, very fast advancement, whereas Brazil is much slower. And if we move back again here, and we put on trails on them like this, you can see again that the speed of development is very, very different. And the countries are moving more or less in the same rate as money and health. But it seems you can move much faster if you are healthy first than if you are wealthy first. And to show that, you can put on the way of United Arab Emirates. They came from here, a mineral country. They catch all the oil, they got all the money, but health cannot be bought at the supermarket. You have to invest in health. You have to get kids into schooling. You have to train health staff. You have to educate the population. And Sheikh Zayed did that in a fairly good way. And in spite of falling oil prices, he brought this country up here. So we got a much more mainstream appearance of the world, where all countries tend to use their money better than they used in the past. Now, this is more or less if you look at average data of the countries. They are like this. Now, that's dangerous to use average data because there's such a lot of difference within countries. So if I go and look here, we can see that Uganda, that today is where South Korea was 1960. If I split Uganda, there's quite a difference within Uganda. These are the quintiles of Uganda. The richest 20% of Ugandans are there, the poorest are down there. If I split South Africa, it's like this. And if I go down and look at Nigeria, where there was such a terrible famine lastly, it's like this. The 20% poorest of Nigeria is out here, and the 20% richest of South Africa is there, and yet we tend to discuss on what solutions there should be in Africa. Everything in this world exists in Africa. And you can't discuss universal access to HIV for that quintile up here with the same strategy as down here. The improvement of the world must be highly contextualized. And it's not relevant to have it on regional level. We must be much more detailed. We find that students get very excited when they can use this. And even more policymakers and the corporate sectors would like to see how the world is changing. Now, why doesn't this take place? Why are we not using the data we have? We have data in the United Nations, in the national statistical agencies, and in universities and other non-governmental organizations, because the data is hidden down in the databases. And the public is there, and the internet is there, but we have still not used it effectively. All that information we saw changing in the world does not include publicly funded statistics. There are some web pages like this, but they take some nourishment down from the databases, but people put prices on them, stupid passwords and boring statistics. And this won't work. So what is needed? We have the databases. It's not a new database you need. We have wonderful design tools, and more are added up here. So we started a non-profit venture, which we called Linking Data to Design. We call it Gapminder, from London Underground, where they warn you, mind the gap. So we thought Gapminder was appropriate. And we started to write software which could link the data like this. And it wasn't that difficult. It took some person years. And we have produced animations. You can take a data set and put it there. We are liberating UN data. Some few UN organizations, some countries accept that their databases can go out on the world. But what we really need is, of course, a search function. A search function where we can copy the data up to a searchable format and get it out in the world. And what do we hear when we go around? I've done anthropology on the main statistical units. Everyone says it's impossible. This can't be done. Our information is so peculiar and detailed, so that cannot be searched as other can be searched. We cannot give the data free to the students, free to the entrepreneurs of the world. But this is what we would like to see, isn't it? The publicly funded data is down here, and we would like flowers to grow out on the net. And one of the crucial points is to make them searchable, and then people can use the different design tool to animate it there. And I have a pretty good news for you. I have a good news that the present new head of UN Statistics, he doesn't say it's impossible. He only says we can't do it. And that's a quite clever guy. Huh? So we can see a lot happening in data in the coming years. we will be able to look at income distributions in completely new ways. This is the income distribution of China, 1970. This is the income distribution of the United States, 1970. Almost no overlap. Almost no overlap. And what has happened? What has happened is this, that China is growing, it's not so equal any longer, and it's appearing here, overlooking the United States, almost like a ghost, isn't it? Huh? It's pretty scary. But I think it's very important to have all this information. We need really to see it. And instead of looking at this, I would like to end up by showing the internet users per 1,000. In this software, we access about 500 variables from all the countries quite easily. It takes some time to change for this. But on the axes, you can quite easily get any variable you would like to have. And the thing would be to get up the databases free, to get them searchable, and with a second click to get them into the graphic formats where you can instantly understand them. Now, the statisticians doesn't like it because they say that this will not show the reality. We have to have statistical analytical methods. But this is hypothesis generating. I end now with a world. There the internet are coming, the number of internet users are going up like this. This is the GDP per capita, and it's a new technology coming in, but amazingly how well it fits to the economy of the countries. That's why the $100 computer will be so important. But it's a nice tendency. It is as if the world is flattening off, isn't it? These countries are lifting more than the economy. And it will be very interesting to follow this over the year, as I would like you to be able to do with all the publicly funded data. Thank you very much.
So hope you liked it.
Yeah, very nice video, sir.
Yeah. So you can see that one of the things that we can learn from the way, manner of depiction.
Yes.
Is that we are used to simple x versus y kind of graphical depictions.
Yes.
But you
Yes.
see what he has done is there's x-axis, there's y-axis. So x-axis could be like say per capita GDP or something like that. Y-axis could be child mortality. Then for each country is depicted as a disk, and the size of the disk indicates the population, which is another third parameter. Then he shows many countries in the same graph. Then the fourth one is time. So how things change with time. So you have motion, animation in the graph. Then the fifth aspect is so suppose he is depicting like Middle East or Gulf. You click on that disk, it will scatter into many smaller circles, right? And then you can see the kind of fractionated data where you can see all the internal differences, even within that region. So 5 different aspects are all plotted on the same screen, and it tells that whole thing as a story. It just makes it what makes it so interesting and even funny at times. And you can draw conclusions. For example, the rate at which different countries are growing, different regions are growing, you can see in that graphical depiction with animation in the obvious fashion. So this is the kind of innovation that is needed if you want to visualize data. It's not just using some standard mathematical methods, right, to show data. There's a lot of innovation that can happen. So okay, so we'll continue this in the next class. We'll look at some ways of some similarity methods, how you can compare different data objects, and we'll see how we can learn things about data using these methods. Okay, so see you again on Monday.